resume. I should also, very sorry about this. Go to here. Okay, 1 second. Record. 1 second, there is a. What was the chat? There was a chat message. The chat message is gone.
Oh, yeah. I wrote it, just reminding you to record.
Ah, okay.
But then I thought you were recording it, so I deleted it.
Okay, but I had not.
Okay.
So anyway, I have started recording now. Okay, let's see. I had actually started recording and paused it before everybody came, and then I forgot to restart it when I started. But okay, it's just a few minutes. I'm just recalling the thing. Unfortunate. Okay. So there exists. So there is a subcollection C sitting inside Z with M indices and an associated POVM. That's what I wanted to say. Associated POVM. Here is that POVM with M operators, such that if I look at 1 by capital M, M equal to 1 through M, this is really what we want, trace of I minus theta M on rho, C, sorry. So yeah, so rho CM, right? So remember rho Z's were my entire collection. This was my entire collection. But now I have taken a subset C with indices C1 to CM. This is sitting inside Z. So I should put CM here. This is less than, what is that? So that quantity is of interest. So, we are looking at epsilon plus 2 root epsilon plus 4 M D by capital D. Okay. This is what we are getting. So in other words, if M D by D is very small, so it's, let's say, epsilon, then we'll end up getting this to be 2 epsilon plus 2 root epsilon, right? So that means M has to be, so the size of that set cannot be too large. That's what this theorem is saying. And if the size is not too large, then I will throw out a collection for you. That's really what this is saying. And so let's get a feel for what these capital D's and small d's are. Though, so the sigma z's are going to be your conditional typical projectors. So it's going to be something like this, pi rho xn. So you know what is the size of this pi rho xn, and your pi is going to be pi of rho. What is rho? Rho is px of x rho x. Okay, so this is what eventually it's going to be. So we'll calculate. So what is d? D is going to be the 2 power n h of, so I wrote this down last time. It's going to be the trace of this guy. It's going to be this dimension of the subspace, the conditional typical projector, the dimension of the subspace on which the conditional typical projector will project. And capital D also you'll figure out. So we'll come to it. So we did the proof. So what did we do? The proof was something like this. So, we have to identify a subcollection. And I told you this is kind of a random coding argument. So in other words, what we do is that take any collection. Let's take any collection. Let's say, we take a collection I1, I2 to IM. I'm going to cook up a corresponding theta 1 to theta m. I'm going to cook up a corresponding theta 1 to theta m. Now, as you change this, this is also going to change. Now, so for each choice, there is going to be, so let's call this, so the way I'll do it is, let's take a little C. So, okay, so let me, instead of this, so let me take C1 to Cm, and let's call this C. So for every C and theta C, right, there is going to be an error. What is that error? That error is going to be 1 by M equal to 1 through M, trace of I tensor n minus, no I tensor n, minus theta m rho cm. That's going to be the error corresponding to the choice C and the POVM theta C. Okay. Now suppose we pick this C with, say, a particular probability Q of C. Okay. So every collection C, we pick it with a probability Q of C. Okay. So then I can look at this, right? I can look at, you average over the entire choice of collections. So this is a set of all collections. C is the set of all collections. So I'll instead of this, I'll denote it as double C. So it's a big collection of all. It's a big collection of all sub collections. And if I average my error over this, suppose I do this. Right. So as my C changes, this term here will change. This collection will change. This theta m will change. So I'm averaging over the entire thing. Suppose I show this is less than that quantity which I told you, epsilon plus 2 root epsilon plus capital 4 times capital M d by d. Suppose I show this. That means there exists one collection for which this is true, right? Because if every collection is above this quantity, then this average cannot be lesser than this quantity. So there has to be one. That is the approach we will use. The problem is it is very difficult to pin down one collection. So we do an averaging and we show that on an average there is a good code and there is indeed a good code. That's kind of the approach. And we kind of proceeded with this. So let's take a collection C. Let's take a generic collection C1 through Cm. And we defined our theta. So we first defined a lambda m. I don't know whether to use the same notation. I defined a lambda m as, let's say, pi m pi. Okay. So when I say pi m, I actually mean pi cm, because remember, for every z there is a pi z. So my cm is an index inside C, which is a subset of C. So this is one of the z's. So I should really say pi cm. So let me say pi cm. Okay. And then I define my theta m to be, I want, theta m has to be a POVM. So when I add them, I have to get the identity. But here, I have no clue, whether I'm going to get the identity when I add these lambda m's. So let me do a normalization. That's all I'm doing. But, we need POVM to be self-adjoint, which means, I can't just write like this. I can't write lambda m plus summation m hat not equal to m. I'm just writing these separately, m hat. I can't just do this. If I do this, it's not self-adjoint, right? Neither can I place this to the left, nor can I place this to the right. So what I do, I'm going to do a minus 1 by 2, minus 1 by 2. That's all that's really going on. But, I have this big beast with me and I have to somehow deal with this, right? So now what am I looking at? I am looking at a trace of I minus theta m. What is theta m? Theta m is this beast. So I will call for, use later on, I will call this S and I will call this T. I hope I did that. So S plus T whole power minus half. This is S again, and S plus T whole power minus half. I have this applied on rho Cm. I was looking at this. And then I applied the Hayashi-Nagaoka. I'm not going to write the Hayashi-Nagaoka simply says this. Hayashi-Nagaoka simply says this. If S and T are two positive semi-definite operators, with S being sandwiched between the zero operator and the identity. Furthermore, if S is not just positive semi-definite, but it is also dominated by I, then I have this beastie term on the left. I'll give you a simple expression for that, is what Hayashi-Nagaoka give. they say this into s plus t whole power minus half. This whole operator is dominated by the operator 2 times I minus s plus 4t, a very, very popular inequality in quantum information theory. So we will do exactly that. So using the Hayashi-Nagaoka, we get two terms, right? So this is term 1, T2 by M trace of, sorry, there is an M here, summation M equal to 1 through M. Sorry about this. M equal to 1 through M trace of I minus pi M pi. So again, I'm writing this pi Cm. This times rho Cm. This is the first quantity plus 2 by M equal to 1 through M. There is a T here, and our T is all the elements other than lambda M. So it's going to be something like this. Trace of M hat not equal to M, lambda M hat. Lambda M hat has that big term. This is your lambda M. Okay, this is your S in some sense. Lambda M hat rho Cm. Okay, so I will just elaborate on this. So this is copy, paste. So this is so the second term, by linearity, I'm going to pull this thing out. I'm going to pull this term out, and this lambda M hat is essentially pi. So I'll be careful here. Pi C M hat. So M hat is not equal to M, pi rho Cm. Okay, so let me just pause here if there are any questions so far. Put a thumbs up. If you have any question, please ask me. Otherwise, just put a thumbs up. Okay, cool. So let me get ahead. So we did the first term. So we recall we did the first term. What we did, so let me see how much I had. I kind of looked through this. Yeah. So we had, this is exactly the analysis. So I'm not going to go through the first term. I'm going to go through the second term. Okay. So second term. Observe one point. I talked about random coding in the sense I'm going to choose this collection randomly and then show you that the average over the collections is small, but I really did not use that at all. I haven't done anything so far. I have actually just, kind of looked at the, for a particular collection itself, I just used the hypothesis and so far I've shown. So now I will actually do random coding. Okay. So the idea is the following. So I will show that suppose I take a random subcollection C. So what do I mean? I pick one random element C1, another random element C2, and M such elements. So what do I do? How do I do this? Remember, I have Z, right? So Z is a bunch of all indices, and I have a distribution on Z, right? So I will pick the first element with this distribution PC. So I'll just use randomly sample. So think of the following. Think of, say, Z is, say, 100 indices. So 1, 2, 3, all the way until 100. Okay. And I have some distribution. So let's for simplicity assume that the distribution is uniform. So all indices is 1 by 100. And I want to choose a collection of size M equal to, say, 15. What do? I will pick one among these guys uniformly at random. I might get an index 23. I put it there. I'm going to pick one of them uniformly at random. I'm going to get an index, say maybe 74. I put it. And so far I populate, 15 indices. Now, when I populate these 15 indices, I can associate with that theta 23, right? What is theta 23? Theta 23 is just, theta 23, what is theta 23? Theta 23 is just, lambda 23 plus lambda 74 all the way until lambda 47 whole to the power minus half, lambda 23, and then this again comes here and I have minus half. What is lambda? What is any lambda? What is lambda 74? Well, lambda 74 is pi 74, pi 74, pi. What is these? These are given by the hypothesis of the packing lemma, right? Each fellow has been given. The packing lemma gives you a collection sigma 1 to sigma 100. It gives you a collection pi 1 to pi 100. It also gives you an ambient pi. So all this I can cook up. So I have this collection. So now what do? I will evaluate trace of I minus theta m rho cm. I do this 1 by m summation m equal to 1 through capital M, right? So here my m is going to be 15. I have 15 words. They are 23, 74, all the way until 47, right? And then what is the probability of these? What is the probability of getting this collection? Well, I pick this with 1 by 100, pick this with 1 by 100, pick this with 1 by 100. What is the probability of this? Well, it's just 1 by 100 to the power 15. So now, so this is one term. So this is one term in this big sum. So I have taken one collection and I've evaluated. I'm going to take one more, evaluate, one more, evaluate, and then do an averaging. That's if I then do over all possible collections of size 15. So this is the set of all possible collections of size 15. And if I show this is less than something, then there exists one collection for which it is less than. That's really what I'm doing. I never used that so far, but I'm going to do that in the second term. So let's look at the second term. So what is the second term? Second term is 1 by m equal to 1 through capital M, m hat not equal to m, trace of pi cm hat pi sigma cm. That's what it is. Sorry. Yeah, sigma cm, not rho. If I had written rho, I'm sorry about that. Oh, I have to be. I don't know how nobody asked me. Because my packing lemma, I stored it in terms of sigmas, right? Not the rows.
Like you said, sigma is the same thing as rho xn, you said before.
Yeah, well, it's not the same. This packing lemma is more general, but we will apply it in terms of the rho xn's. You see what I'm saying? Yeah. Okay. Okay, so this is the term. Now, what do? We are going to do, okay, so first thing, 1 by m equal to 1 through capital M, m hat not equal to m, trace of cyclicity of the trace. I can say this, cm hat pi sigma cm pi. Okay. Now I use the approach of random coding. Okay. So every collection, every collection C, I pick by choosing each of the indices C1 to CM, each of the indices independently and IID according to the distribution PZ. Okay. So just like I explained in the example. So if I take a collection C, and if I take two elements, let's say C1 and C23. So there, this is the first index, this is the 23rd index. What is the probability? What is the probability that my first index C is say 10 and C23 is say 74? What is the probability? Well, it is just the probability of picking. So it is just the PZ of picking 10 times PZ of picking 74, because I've chosen each index of that subcollection randomly, independently, according to the distribution PZ. That is my distribution on the collection. So I'm going to now look at the expectation. So expectation of the error is kind of the average error. So I'm looking at the expectation of this quantity. The expectation is over the choice of the code. So, at any step, if you don't completely understand, please kind of stop and I'll kind of explain. Okay, this is the expectation. So this guy is random, this guy is random, and independent and IID, right? So what is this? This is, so what is the expectation? Expectation is you take the value and you hit it with the probability. Probability of choosing CM hat and CM, right? What is the probability of choosing CM hat and CM? Well, probability of choosing CM hat as Z hat, and CM as Z. So PZ of Z hat, PZ of Z. So I should be writing it like this. Pi CM hat is Z hat, pi sigma Z pi. I will just pause and let me know if you don't understand this step.
So two code words can be the same, right? C1 and C2 can be the same, for example.
Yeah, that is why my Z hat could overlap. No problem with that. So this is just like I did this 1 by 100 to the power 15. Only thing is here, only there is only two terms here. So the rest of the summations knock off, and I will just have 1 by 100 square. There it was uniform distribution. That's why you have 1 by 100 times 1 by 100. But otherwise, what is the probability of Z hat and what is the probability of Z? That's all I've done here. Okay, I'll continue. So I'm just going to pool all the summations together. 1 by M Z hat. I'll push the Z summation and the linearity. So I will just look at this and note that there is no problem. Sorry. PZ of Z hat, I keep it as is, but I push the okay, what have I done? Observe, this is the only term that depends on Z. PZ is a scalar. So I can just first push it all the way till here. Once I push it, observe that none of the terms, none of these terms depend on z. So I can push the summation z all the way till here. That's really all that I have done. Okay. Now, what is summation pz of sigma z? Well, that's exactly what we were told to be sigma. So this is m hat not equal to m pz of z hat trace pi z hat pi sigma pi, because sigma is z pz of z sigma z. That's what this is. Now we have one hypothesis, that is pi sigma pi is at most 1 by capital D times pi. This is the fourth hypothesis. So we will use that, and we will dominate the term on the right. That is the last, these operators. So I have 1 by m z hat m hat not equal to m pz of z hat trace pi z hat times pi by d. D is a constant, so I can pull it out of the summation. So 1 by m times 1 by d z hat m hat pz of z hat trace pi z hat pi. So just one thing, when I'm kind of going here, I'm really using the fact that trace. So I'm really, how do I argue? One second. How do I argue this step? This step is argued as follows: trace AB is greater than 0 whenever A and B are greater than 0. Remember, you can't say AB is greater than 0, but you can only say the trace is greater than 0. So this is true. And since pi by d minus pi sigma pi is positive and pi z hat is positive, I can say trace of pi by d times pi z hat minus pi sigma pi z hat. This is positive, and so you'll kind of get this step. Okay, so I end up here. Okay, now I know I is greater than pi, or rather, so let me just say 1 by m times 1 by d z hat m hat pz of z hat trace pi, instead of pi z hat pi, I can put an I here because I dominates a projector. So this is because pi is dominated by I. So that gets me to 1 by m times 1 by d z hat m hat not equal to m pz of z hat times trace of pi z hat. I'm just writing another step just for clarity. Paste. So pi z hat, we know hypothesis, right? The hypothesis says that each sigma z, remember, there is a subspace. I can identify a subspace for you. If you can identify a subspace where each of the guy overlaps a lot, I mean, I can identify for each sigma z as subspace in which it lives almost completely. And furthermore, you have a good tight bound on the size of that subspace, right? We had these two hypotheses in the beginning. So this, we use the second hypothesis now to upper bound the last term above. So z hat m hat not equal to m pz of z hat trace by z hat is d. So it looks like all the terms are now in picture, right? Because I can pull, I can sum over z hat first. So let me just do m. The m and the none of the terms really depend on the m and the m hat. So I can say m times 1 by m times 1 by d times m minus 1, right? Because m times m minus 1. And I have a sum, I'll get the d also out. And I have just a summation over pz of z hat. And that's just going to be 1. So 1 by m d by capital D times m into m minus 1. So that is at most m. One of the m goes, and then the m minus 1, I'm not going to worry about it. I'm just going to say m d by d. So the second term is indeed at most m d by d. So what have I shown? I have shown the expectation of the second term. Well, I can say the first term I've shown for every term, so the expectation also has to be less. So expectation of the first term and the plus the second term, this is at most epsilon plus 2 root epsilon plus m d by d. So that means there exists a collection. That's exactly what the packing lemma says. It also doesn't give you a collection. There exists a collection of size of cardinality m. So there exists a collection C sitting inside the set of all possible indices Z of cardinality M, with particularly C equal to C1 all the way until Cm, such that and a corresponding POVM theta 1, theta 2, all the way until theta m. So I have this 1 by m equal to 1 through capital M, trace of I minus theta m rho Cm is at most epsilon plus 2 root epsilon plus capital M d by d. This epsilon comes from the conditional typicality. This comes from the gentle measurement lemma, and this comes from the argument above. Questions, or I will pause for a minute or two. I'll just get some water. Is it okay? Okay, cool. Okay. Okay, good. So, okay. So what are we looking at? We're kind of looking at this, right? So we have our row xn's. We have our row xn. These are all our possible preparations. H tensor n. These are all our preparations, but these are all not orthogonal, so I cannot distinguish them. So I'm looking for a collection C, right? But I also know, so let's not take inside xn, let us take inside T delta n with some px. Okay, So for these guys, why did I do that? Because for these guys, I know there is a pi xn, pi rho xn, such that what happens? I know trace pi rho xn and rho xn, they overlap a lot. I know this. I also know that these trace pi rho xn's are less than 2 power n this quantity a p x of a s of rho a. Actually, I have not posted the homework yet, so I should do this. S of rho a. This I know. So two parts of the hypothesis are in good shape. So there is one kind of a missing link, but let us just kind of assume the following. So let us just, there's a small technicality here, which for which I'll actually give you a slightly different proof, but let's just assume this. Okay. See, if I sum over xn, I know this is rho tensor n, right? But we have chosen only our z to be this in some sense, the t delta npx, because we need this. And we are not guaranteed if xn lives outside. We're not guaranteed all this. So that means I should take a distribution on t delta npx. But this distribution is a distribution on xn. Okay, so there's this little bit of fudging. Let us just say this is t delta npx, and let us just say this is rho tensor n. I know there is a projector pi on rho tensor n, an ambient projector, right? And I also know if I do pi, rho pi, remember this is one of the statements of unconditional typicality. This is covered in one of the, there's an operator inequality I told you. This we know. This is 1 by 2 power n s of rho tensor n pi. This is one of the elements of the typicality proofs. So we have the first. This is the first hypothesis of the packing lemma. This gives you the second hypothesis of the packing lemma. This gives you the fourth hypothesis of the packing lemma. The only one we don't know, and I told you this is the difference between conditional classical typicality and quantum typicality, is we do not know this, that the projector of the unconditional, that is the projector of rho tensor n, does that also overlap these guys heavily, right? We don't know this. And I told you this was kind of the difference, remember I actually made this, here it is. Yeah, here it is. So this was, in this lecture, I told you that there is this one, it's not clear, it's not clear whether this overlap happens, right? It's not clear whether this overlap happens. And that's one element of the packing lemma that we need, right? Is the reference clear to both of you? Just put a thumbs up if you're clear what the reference is and if everything is fitting in perspective.
Yes, sir.
Okay. Okay. So that means we don't have this part, and we will now prove that. Okay. So this is what is referred to as the pinching lemma. I will just prove that. So this goes back to your typicality, and you might at that time wonder why I'm doing this, and why is what is non-trivial. So remember, in the classical, if yn is in the conditional typical set of pxy given xn, then this naturally implies that yn is individually typical. So you don't have to worry about this, but that is not clear in the quantum case. So we will prove this. Okay, so what am I proving? I'll explain what am I proving. So this is, I will also give you the reference of the book where I'm doing this. I don't know whether he refers to it. I think he refers to it as pinching lemma, but anyway, I'll do it. Okay, suppose rho x's are a bunch of density operators. Px is a PMF on X. Okay. Let rho x's have a spectral decomposition Qy given X of Y given X. Ey given X. We remember we just wrote it this way so that it's convenient for us. And I particularly used a different Q here. Okay. And so we define our conditional typical, recall the conditional typical projector. So pi xn, or I'll say rho xn, is you take all those ey1 given x1 tensor all the way until v eyn given xn. I choose only those yns such that xn comma yn is typical according to the classical notion T2 delta n px times qy given x. This was our conditional typical projector. So I sum over all yn here, but include only those terms to the indicator function. And we showed that if xn belongs to T delta n px, that is the sequence is typical as in as a sequence in itself. I have something like this, right? I have something like this. Trace pi rho xn overlapping with rho xn is very large, 1 minus exp minus n times something. I'm not going to write that something. This is what we know. But now I'm doing something else, right? I'm now taking rho. Rho is, I average my rho x's with that distribution rho x. Suppose rho has a spectral decomposition. Rho is summation. So it is not py, it is not qy, it is some. So you kind of, you just you average this with px, you're going to get a density operator, and then you do the spectral decomposition. You're going to get some weird, weird spectral decomposition. I have no way how to relate R, Y, Q, and P, and E, and F, right? So I end up getting this. Now, if I just look at the unconditional typical projector of rho tensor n, this is going to look something like this. I'm going to say y hat n, just because I want to keep the summation of indices separate and not make any mistake. I'm just going to call it y hat, y1 hat, all the way until yn hat. And what are all those y hat n's that I take? Well, I'm going to take that are typical with respect to this distribution Ry. I'm not going to, I'm not going to take this distribution, compute the marginal, and then, look at that. No, I'm not going to do that. All that I'm going to do is find rho, do the spectral decomposition, and whatever R I get, I'm going to do with that, right? So this projector is a completely different beast, and rho xn is a completely different animal, right? I mean, in some sense, they're related, but the relation is not apparent. Y hat n is a typical guy according to Ry, not Py, not Qy, but Ry. Okay. And now what am I looking at? I'm looking at, does this guy overlap greatly with any rho xn I take to be in T delta npx? Will this guy overlap? So I'm just going to put it 2 delta here. Okay, just for clarity, 2 delta here. So that's this overlap. Not at all clear, but let's see. So let's compute it. So I am doing. So I have, so what am I doing? I'm looking at this. So I'm going to write this. I'm going to write this and then pause so that you agree with me. So y hat n. What is this? Y hat n belongs to T2 delta n py. Sorry, not py, ry. Fy tensor all the way until Fyn. Fy1 tensor all the way until Fyn. Okay. Now I have our rho xn. So that is this term. I'm just going to, instead of having to write it again, I'm just going to copy paste. So I have this, but my yn will sum on, my yn will sum over all yn. No, my yn will sum only over. Oh, sorry, I should not have copy pasted this. This is the wrong one to copy paste. I should take rho xn. Rho xn is the following. Rho xn is yn belonging to yn, qy given x of yn given xn, ey1 given x1, all the way until eyn given xn, ey1 given x1, all the way until eyn given xn. This is what it is. Okay. So let's come. So what is the trace? So remember, trace of A, B, C, D. Trace of this is essentially B, C, D, A. Okay. So from that, I can write this as follows. Yn belonging to yn, y hat n belonging to T2 delta n ry. Okay. Q y given x n of yn given xn, that term is as is. Now I'm going to do a little bit of copy pasting. I copy and paste this with the, so this is my operator, product of operators. Now this one will go right. That's it. So I just took the term on the left to the right. That's what this is. So what is this? I mean, if you look at it, right? This is fy1 through fyn and ey1 x1 till ey and xn. This is just the complex conjugate of that. So what am I looking at? I'm looking at something like this. Copy, paste. So I'm looking at mod square. Somehow I want to show this overlap as high, right? This is my goal. So there is a trick here. Oh, there is one issue in my, nobody pointed this out. I don't know why. See, there is a y hat here. These are all y hats. Because I used my pi, I wrote y hat here, but I did not write it here. The y hat here. Yeah. Okay, so there is a small trick here, and the trick is as following. So let us define the following. So we have the following, right? Remember, I'll just recall qx, rho x is this qy given x of y given x, eyx, outer product ey given x, ey given x, right? It's rho. This is rho is given by this, right? ry of y in a rank 1 projector on fy. And in particular, rho is summation px of x, rho x. That's what it is. Okay, we'll do one small trick here. So let us define, I'm going to define a new distribution, a completely new distribution. So it is defined as follows. I'll call it, I want to use a different letter, completely different letter. So let's say I'm going to use the word G. G is a distribution, okay? Don't get confused with the unconventional use of the word G, but just let's say G. I'm going to define it on a new distribution on y cross x. I'm going to define a new distribution on y cross x, and it will be denoted as y hat x. So what is y comma y hat x, right? I'm giving you a distribution. So what is this distribution? It is px of x times qy of x, the same thing as we saw so far, times this quantity f y hat ey given x. I'll just kind of bear with me, and we'll see how it goes. So I defined this new distribution on y cross x. Is this a distribution? So what are, when I have a distribution, what all should it satisfy? It should all the terms should be non-negative, and when I sum it, I should get 1. Right? Let's check that. So clearly all the terms are non-negative, because this term is non-negative, this term is non-negative, this being the norm, this is non-negative. So indeed all the terms are non-negative. Do they sum to 1? Let's check. So let's, so what I want to show x y hat of g y hat x y hat x. This I want to show is 1. Okay, so let's first sum over y hat. Doesn't matter in which order you sum, right? So let's just sum over y hat. So g y hat x of y comma y hat comma x, right? So what is this? I'm going to get px of x qy given x of y given x, summation over y hat fy hat squared fy hat, sorry, ey given x, right? What is this term?
Just one. It's the norm
of norm of ey given x. This is the norm of ey given x, because you're looking at the sum of the coefficients when expanded in terms of the basis Fy hat. Okay. So recall Ey given X can be written as sorry, this can be written as yeah, this can be written as like this. So when I sum the norm squared of this, I'm going to get 1. That is the norm of this. Okay. So what I get, this is, so when I add, so the this term is essentially Px of X Qy given X of Y given X. Now clearly when I sum over X and Y of this term, clearly I'm going to get 1. Right. So this is also satisfied because Px is a distribution and Qy given X, when I sum over Y, I'm going to get 1 and then I'm going to get 1 again. Okay. So this is indeed a distribution. Great. What else can we say about it? So let's look at, so G, I'm going to just copy paste that. Okay. So what is the marginal GYY hat? Sorry, GYX. What is the marginal GYX, Y comma X? Well, this is indeed Px of X, Qy given X of Y given X, because I'm going to sum over Y hat, I'm going to get 1 here, and that's really what we get, GYX. Okay. Next, what is the what is G Y? What is GY hat? What is the, 1 second. Yeah, what is GY hat? What is the marginal GY hat? That's not clear. That's absolutely not clear. Right? GY Y hat of Y hat. What is this marginal? Let's check. Okay. So what am I doing? I'm summing over X and Y. Let me, so far, let me just pause. If there are any questions, ask me. I don't want to go beyond, if something is unclear. If I keep going, it'll get more unclear. And there are 2 of you, so I can have if some of you are not kind of comfortable with something and don't want to ask in the middle, I can have a session tomorrow. Definitely I can have a long session. Today also I can just meet up after class. So far everything's okay. Just put a thumbs up. Everything's okay so far. Hopefully it's clear to you what I'm doing, where I'm going, the trick, the steps I've kind of started to do. Okay. So I'm doing the marginal. What is this marginal GY hat? So I'm doing this, right? Px of X, Qy given X, Y given X of this term. But this term I can write it like this. Can I write it like this? Fy hat. It's an amazing thing you will see now. So just kind of bear with me and Fy, right? Just writing the same thing differently. Can I do this? Can I get the Fy hats out and push the scalars inside? X. So just tell me if you will permit me do this. If this step is okay, put a thumbs up. Okay. What is this guy?
Rho of X.
Yeah, so let's do it. X, Px of X. That term in the middle is rho X. Now what is this?
Rho.
Now what is this? Recall what is rho. So what is this?
R of y hat.
Yeah, Ry of y hat. Correct? Agree?
Yeah.
So I have created an interesting distribution G y hat x, right? Its marginal is y hat marginal is Ry of y hat, right? This is correct. If I look at gxy of x comma y, this is px into qy given x. If I look at gx, it is px, right? So now let us remember, why did I do all this? I ended up in this step and I said I'm going to take you through some trick, right? I ended up in this step and I said I'm going to take you through some trick. So I've ended up here. So I'm going to copy paste this and use my G now. Okay, so I'm going to copy paste this and use my G now. So what is this? I'll just go step by step. Yn belonging to Yn. Y hat n belonging to T2 delta n Ry. Qy given x, n of yn given xn. Can I write this as product I equal to 1 through n f y1 hat yi hat g yi given xi? Sorry, e yi. All that I'm doing is that big norm of that big dot product, the norm of that big tensor product. I'm writing it as product of each of the norms. Okay, so remember EY1 tensor EY2 into GZ1 tensor GZ2. This is essentially EY1 GZ1 EY2 GZ2. This is one of the axioms of tensor product. That's all I've done. So I should put a square. This is correct. And this I claim, what is this? So Yn belonging to Yn, y hat n belonging to T2 delta n Ry. Can I say this is, so recall G x y hat is essentially px qy given x times this f. I mean, so let me write this completely. G x y hat of x comma y hat. This is px of x times qy given x of y given x times fy hat ey given x. This was what it was, right? And I observed that gx of x is px. So that means g y hat given x of y comma y hat given x, at any point, if it's not clear, just stop it. This is what g x y hat of x comma y hat divided by gx of x. That's what it is. But that is same as px of x times qy given x of y given x times fy hat given ey given x divided by px of x. So I have substituted for this, and for this I've substituted this. So that means I get qy given x of y given x times fy hat given ey given x norm squared. Do you agree? So let me go over each one of these steps once again, just because, just kind of look at it and stare. I mean, stare and listen. So this is my definition. If I do the marginal, gx marginal, I get this. This is 2. This is 1. Now let me compute this quantity. By definition, this is total divided by the conditioning variable. That's what this is by definition. Now, for the numerator, I substitute 1. That's what is this. For the denominator, I substitute 2. That's what is this. And the px cancel, I get this, right? And if you observe, this quantity is exactly what I have there, right? So I can write this as G y hat given x of n yn y hat n given xn. If you agree so far, put a thumbs up.
So do we know that the Qn is the product distribution of all the Qs?
Yeah, because yeah. So let's go back. So where did we get this right? We got this from row xn. Remember row xn? Yeah, this is our row, and we wrote down row xn. If I do row xn, right, I am going to do a tensor product of all these guys. I'm going to I equal to 1 to n, right?
Row x is that.
Let me do it at the bottom. So let me do it. See, row x is this, right? Row x is qy given x of y given. So row. Do you agree with this? So can I say this? Do you agree with this? I'm just writing with the I, and I'm calling the dummy variable yi. That's all.
Yeah, we just called y to be y.
Yeah. So now row x1 tensor row x2 all the way until row xn. That's your row x. That's your row xn. This is nothing but I put a tensor product of these copy.
Oh, I see. Okay.
Paste. So then I end up getting, so it's like this, right? It's to give an example, let me do this like this. So lambda a ea summation over a tensor mu b fb. So if I do this, right, essentially I'm going to get a b lambda a mu b ea tensor fb ea tensor fb. That's exactly what I've done there.
Yeah, I got it now.
Okay, got it. Cool. So I'll continue. So is this okay? So let me know if there any other question. Let me know. I'll just go and ensure that everything is correct. Okay, so we continue from here. So this is what we get, right? But ry, so what did I show? Ry of y hat is essentially g y hat of y hat. So the marginal, the y hat marginal of g, this is what really I showed here. The y hat marginal of g, unfortunately there are two y and y hats, and the y hat marginal of g is indeed the ry. Okay, so can I do this yn belonging to yn, instead of saying y hat n belonging to t2 delta n ry, can I say g y hat? Because the distributions are indeed the same. How can the typical sets be different? They have to be the same. G y hat of x of yn y hat n given xn. Now I am summing over all yn. if I sum over all yn, I'm going to get this y hat n belongings to T2 delta n g y hat of g y hat given x n of y hat n given xn. Tell me if you understand, if put a thumbs up if you, so far you are with me.
Yes.
Okay. Now, remember, so what are we saying here? This is the unconditional typical set of g y hat. But xn, right? Xn, where is xn? Xn is T delta n px. Right? That's what our xn is. Recall our xn, rho xn. So recall the whole thing that we are trying to do. This is what we are trying to do. And our xn is in T delta n px. Where did I write this? Pinching lemma. Pi rho xn. I don't know where I wrote it. But my xn is in the T delta n px. No, I should have written it somewhere here. Yeah, I have, well, okay. I think I have missed reading that. Oh, here it is. Xn is in the T delta n px. Okay. If my xn was in g delta gx, T delta n gx, then I am done. Do you agree? Because my xn is in T delta n gx, my y hat n is in T2 delta n g y hat, and gx y hat is the distribution I'm taking with respect to which. So it has to be, this has to be greater than 1 minus, exp something. But what is gx? I showed you gx is indeed px. So indeed, xn also belongs to T delta n px. Sorry, gx. Right? Px equal to gx. And hence, all that I'm saying here is if I take one distribution pxy and I take an xn belonging to T delta n px, and I look at this T delta n py of py given x, n of yn given xn, well, I know this is even greater than this quantity, T delta n. If I take the conditional typical set, that conditional typical set is sitting inside py given x of yn given xn. Now, when I know this itself is greater than 1 minus exp of something, then this definitely is also. But now everything is really, I mean, gxy hat is essentially px into gy hat given x. So that means we are in good shape. Okay, so that means that this guy is greater than 1 minus epsilon, and we are done. If you don't get the last element of the argument, tell me. Clear?
Yes, sir.
Yeah.
Okay, cool. So that means we indeed have pi. So we indeed have pi rho tensor n rho xn is also high. This is also high. So which means we have all the components of the packing lemma, and we can essentially prove, use this to kind of prove the capacity theorem. Okay. So I will stop here, but in the next class, I will do, so recall in the earlier class, I motivated the packing lemma by talking about 3 definitions, right? Code, what is the capacity, what is the maximum rate? I think it was, This March, I think 11th. Maybe it is this.
Lecture 19.
Yeah, this one. So I talked about this, and I told you there is a need of probability of error and all that. This is I will actually now prove this theorem in the next class, and the idea is to use the packing lemma, but I might give you an alternate proof. I mean, I will use the packing lemma, but I'll do it in a very subtle way. Okay, so that's it. So I think maybe some of you, because I had too many classes last week, you might have missed looking back at the classes and might be finding it little difficult to catch up. So I will have a kind of a long discussion session tomorrow, kind of going over the material. I can also have kind of something like at the end, after this class gets over. So as of now, that's it. I will just stop the recording, and